All right, welcome everyone to our 2021 seminar series. So we are really pleased to get this started with Dr. Keahey. Dr. Keahey is a research scientist and a scientist at the Argonne National Lab and a senior fellow at the Computational Institute at the University of Chicago. And I came to know Kate for I think quite some time ago, and I was involved in this NSF Genie project. This date back to many years ago, I think, at least 10 years ago. And she came in as an expert in the infrastructure as a service, and she did a lot of fantastic work. And actually that geared the ONSF, the cyber infrastructure, to create this Chameleon project. So let me just introduce, not to deviate too far away from the script here. Dr. Keahey is one of the pioneers of infrastructure cloud computing, and she created the Nimbus project. And it's the first open source infrastructure as a service implementation. And she's been working in this field and apply that concept in the scientific data centers and applications to facilitate such research for the community at large. Kate leads the Chameleon project. I hope all of you actually know the Chameleon project, one of these NSF cloud, one of the two NSF large-scale NSF cloud projects. It's a deeply reconfigurable, large-scale, open experimental platform for computer science research. To foster the recognition of contributions of science made by software projects, Kate also co-founded and now serves as a co-editor-in-chief of the Software X journal. It's a new format designed to publish software contributions. She's as I said, she's a scientist at Argonne National Lab, a senior fellow at the Computation Institute at the University of Chicago. Let's give a warm welcome of Kate. Thank you for coming to Computer Science. How are you?
Thank you very much for a lovely introduction, and thank you for inviting me to come. I'm always delighted to talk about Chameleon, and I'm hoping that I can recruit from among some of you new Chameleon users or old Chameleon users, as the case may be, for either research or education projects. So let's get started. Chameleon is a collaboration between four fantastic institutions: University of Chicago, the Texas Advanced Computing Center, which is one of the top 5 supercomputing centers in the world, with the new NSF Frontera supercomputer, RENCI, which of course is leading the Fabric project, building a very innovative and really groundbreaking networking testbed, and Northwestern University, the place where Starlink resides, which seems to be connecting all the networks worldwide. So a quick summary of what Chameleon is, if I can only figure out, oh, yeah, no, there we go, it does advance. So Chameleon in a nutshell. So first of all, everybody knows chameleons like to change, right? So why are we called Chameleon? It's because we like to change. We like to reconfigure our resources in such a way that they are just perfect for your experiment, right? So we support deep reconfigurability at bare metal level. And we also support isolation between experiments, right? And that goes not just to bare metal when you do experiments on nodes, but also in networking. Users have a lot of power on the nodes that they execute on. They can power them on, power them off, can reboot them. They can boot from custom kernel and get serial console access. And the trick in Chameleon has always been to balance a large-scale investment in homogeneous hardware that allows you to run experiments at scale, like high-performance experiments, and the investment in diverse hardware, so cover as many different hardware configurations, and in particular as many innovative configurations as we could. So we've got large-scale hardware, we've got something on the order of 1,000 nodes Out of this, about 500 are in large homogeneous partition. We've got a total of 6 petabytes of storage, and that's both for storing your images and your experimental data. And then we've got it all distributed over 2 sites, University of Chicago and the Texas Advanced Computing Center, connected with 100G network. So you can actually run 100G large flow experiments. But then we also have investment in diversity. So we've got ARMs and atoms. We've got quite a few FPGAs, and we're going to be buying a lot more and newer ones. And we've got many different types of GPUs, very, very popular with our users who are looking at various data science questions. We have Corsa switches, which allow you to create your own network controllers, very, very important. And we've got a bunch of hardware that we are just putting in the pipeline and just buying, and I will talk about that later because phase 3 of Chameleon just started. Something that is unique about Chameleon is that it's configured using mainstream cloud technologies, right? Unlike test beds that came before it, that were generally speaking configured using something developed in-house, so academic software. Chameleon leverages OpenStack, right? And that gives us access, that allows us to work with large community, gives us access to all the innovations and contributions that they make, and that allows us also to contribute to what they do, right? So in other words, whatever we come up with has a much larger audience as well. Right, so in particular, for example, we contributed a component that does advanced reservations called Blazar, and in 2017, it's been recognized as official OpenStack component, right? So an outsized contribution for a very small but punchy academic team, right? So I'll talk about OpenStack some more. And of course, we live to serve, right? This is an open testbed. Anybody can run, anybody with a good computer science research project, and it's a production testbed for computer science research, right? It started in 2014. It went into production at the end of July 2015, and it was recently renewed for 4 more years, right? So there's going to be Chameleon until the end of 2024. We currently have over 5,000 users working on almost 700 projects, recruited from 100 institutions, who contributed over 300 publications. So just quick vital stats of Chameleon. So now drilling into this a little bit further, Chameleon is a shareable instrument. So what is a shareable instrument? You can think about it as an instrument that has 2 dimensions. First of all, it supports research functions, right? So in other words, it's an instrument, a scientific instrument for the experiments in computer science that you want to run. But secondly, it has to support not just those research functions, but also sharing functions. So it has to be able to accommodate as many experimenters as possible without detracting from their research. And if you think about it, sharing research functions are supported by things like how much hardware you have. So one thing that I'm very interested in feedback on is the hardware that we're buying for Chameleon right now. Is it going to be enough to support your experiments? Well, expressiveness, how do you get at that hardware, right? Can you specify, can you only say, you know, I need a GPU, or can you say, I need a GPU of a specific type, a V100 type with NVLink? Or can you say, I need this particular node because I'm running power experiments and I'm concerned about variability, right? So I want to have the same consistent baseline for my experiments. Configurability, right? Can you provide bare metal reconfiguration? Can you provide network stitching? Can you configure that tool to support the needs of your experiment? And then the sharing functions, how many users we can experiment. You can think of automation and isolation, right? So you need to provide some sort of isolation between users so that their experiments don't impact each other. Automation makes it easier to use. Usability in general, very important to support more users with perhaps less experience. And familiarity is a very good thing, right? Familiarity means that as soon as you come, you're kind of familiar with the tool and you can get started. So if you think And put it in context, those two measures give you some examples of how different types of resources fare within those dimensions. So if you think about traditional HPC resources, batch operated, you submit jobs to them, and you can do some computer science research on that, but not a lot. On the other hand, they are very efficient, very easy to use, and support a lot of users. Better, if you go to virtual clouds, you could do experiments with custom kernels on virtual clouds, right? So that's very, very good. And they are a little bit harder to use, but that's okay. If you think about something like Chameleon, well, you can not only support custom kernel experiments on Chameleon, but you get bare metal. So that means that you get performance that is very isolated, and you can do experiments with power management, performance variability, and things like that. And then lastly, you can think of custom test beds that were built perhaps on hardware level to support your needs, but that's just for you, right? So there's a trade-off sometimes between how many experiments you can support and for how many people. Now in Chameleon, we posit that there's a third dimension to all this, which is shareability. How effectively you can share your experiments and your research. And the factors that influence that is how well you can package your experiments so they are understandable to others, and how easily you can publish them and then discover them. And then throughout the talk, I will talk about all those various different dimensions and where Chameleon sits within them. So first of all, as far as the hardware goes and the experiments that we support, this is what we started out, right? So we started out with 12 racks of Haswell, some at University of Chicago, some at TAC, 3.5 petabytes of global storage system, and lots of heterogeneous hardware. Then in phase 2, it turned out that people actually didn't need that much of a scale, but they needed newer architectures. We added racks of Skylakes, 2 at University of Chicago, 1 at TAC, and then more recently 1 rack of Cascade Lake. We added more storage so that we have storage on both sides. And then, very important, we started federating with others, started federating with Genie, and more recently, we provided a federation mechanism so that you can run experiments over Chameleon and commercial clouds. You could even run L2, layer 2 networking experiments between commercial clouds and Chameleon, and commercial clouds, especially as they are available via CloudBank, which is, of course, an NSF-funded initiative to make access to commercial clouds easy. In terms of heterogeneous hardware, we've got a very large investment in GPUs, and we keep upgrading them. We've got anything from V100s, which are those very expensive, very sophisticated in terms of performance GPU units, to RTXs, which are the gaming GPUs. We've got different types of FPGAs. This is in particular where we're going to be investing more with Chameleons and ways to use them. We've got a collection of NVMEs and SSDs in nodes that are specifically configured to allow experimenters to experiment with different caching layers and different memory hierarchies. We've got InfiniBand, ARMS Atoms, and low-power Xeons for folks who want to experiment with power management. And this is just summarizing what I essentially just said. More interesting is what's coming up with this next phase, which I said Chameleon just got extended for. Part of that is, of course, we're going to be exchanging our old servers, so our Haswell, our investment in Haswells, to new servers, right? The Haswells are still going well, so we're going to be keeping some of those, but some of them are exchanged right now for Cascade Lakes, right? So at TAC, this is happening right now. By the end of the month, we're going to have a big announcement that we now have racks of Cascade Lake at TAC. In a couple of months, we will replace all our Haswells with Cascade Lakes at University of Chicago. We'll be buying more accelerators. All our GPU systems are very, very popular. We're buying more V100s. We're going to buy AMD GPUs. And we're going to buy also Xilinx and other FPGA units, right? So there's still, the jury is on what specifically we buy, and I'm open to suggestions, but there's definitely going to be a significant investment there. We're also investing into storage hierarchy options and buying nodes with Optane, very, very expensive, but everybody wants to experiment with it. and then a mix of enterprise NVMEs and consumer level SSDs, right? Again, a mix in various different quantities, so you can repeat your experiments, you can try your algorithms on different brands of storage. And then we're trying to provide the platforms for experiments that need composable hardware. And we're going to do it in two ways. So at University of Chicago, we're going to have rack with InfiniBand, and that rack is going to contain all of our GPUs and all of our storage nodes. So all this Optane and NVMEs and SSDs, all of that is going to be in that one InfiniBand rack, right? And so that allows people to have RDMA access between those units and do interesting configuration experiments. But then also, we're buying Liquid, where you can do a similar thing, but in a more integrated fashion, right? So that's probably going to come out in year 2. The University of Chicago investment will come in year 1. For networking, we're replicating the fabric design, which is composed of these hanks, which essentially consist of a patch panel. Then you have a variety of interesting switches behind that patch panel. And you can get patched to use this or that switch as the needs of your experiments dictate, right? So we're going to put our Cursor switches behind that patch panel. We're going to invest in various different P4 switches. You're going to be able to construct interesting networking experiments. And then last but not least, we will buy and we will create methods to access Internet of Things devices, edge devices, right? Because there is a lot of interest in working with edge right now. We in fact work also with the NSF-funded SAGE project, which deploys IoT devices for various domain sciences. We want to deploy those IoT devices for computer scientists so that they can experiment with them. And we do have a modest amount of budget reserved for strategic reserve. So if there's something I did not name and you're particularly interested in, please talk to me. This is just a quick graph showing the hardware usage if you're interested, and it shows you what percentage of nodes is available, what percentage of time, right? So the closer you get to this corner here, the more in demand you are. The more you're in this corner here, the less in demand you are. So if you look at this, it looks like, unsurprisingly, all of our GPU nodes are the most utilized things, closely followed by our storage hierarchy nodes. And then there's Compute Haswell and Skylakes. And then the least utilized is the power management hardware, where of course also needs to be supported. Those are very important experiments. It's just that not many people are really utilizing them. And if you're interested more about how Chameleon is built and used and various other statistics about the system, there's our Usenix ATC paper from last year where all of that data can be looked at. All right, so this is—
Okay, can I have a question?
Absolutely.
So do you have visibility, or what level of visibility do you have on the processes, on the tasks that are running on the nodes and GPUs in particular?
So like, can I tell what people are running there?
Exactly, yes.
I can't really. The visibility that I have is on project level, right? So the way users access Chameleon is they create a project, and in the project say, I'm going to be working on this or that. And then they run, and you know, our support ends on when we deploy their image. What they do with that image, so long as it's not something bad, is up to them, right? I mean, we do, you know, intrusion detection and things like that to make sure that the system is used according to policies. But if you use it according to policies, what you do is pretty much your business.
Yeah, sounds good. So the reason I'm asking is that, so this is a very attractive infrastructure, and it's very good for researchers. It's also a good attractive for adversaries as well. Use it as a proxy to run the attacks, or we know cryptocurrency is super attractive these days, $35,000 per Bitcoin, right? Yes. So I wanted to know whether there is a vetting process for users that are using this infrastructure so that they can make sure that they do not use the GPU to mine cryptocurrency like Bitcoin?
Yeah, so actually cryptocurrency mining is relatively easy to detect because you have to call out to mines. And we didn't have any incidents of people mining cryptocurrency on GPUs, but we did have incidents, and our bare metal nodes in general, but we did have those incidents on our KVM cloud, right? So Chameleon has almost all of it is bare metal reconfigurable, but we do have a couple of racks where we run virtual machines, and that's very useful for educational projects. But what happens with virtual machines is that people very often use images that they downloaded from the internet, and very often forget to change the admin password on those images, right? People who run on bare metal images, generally speaking, use the images that we provide, which have key-based authentication, and all the proper security configurations on them are generally very hard to break into. But it does happen. You know, people mine cryptocurrency. They, you know, we can generally tell if it's like 15 cents that they got, or 17 cents, or however much. And we shut them down, and then we have a security incident process where this goes to. Now, some interesting cases arise when people do security-related projects, and on blockchain and you know, other interesting security things, and maybe are not very specific in their descriptions, right? So very often those are legit projects. But we do detect them sometimes and have some false positives in terms of security incidents. And just as an anecdote, we actually had FBI involved in one of them. So
okay, I have a question, if I can ask you. Yeah, by looking at this hardware usage diagram, so the utilization of this hardware it looks like pretty optimal. Am I right in assuming that? I see that you know, in terms of the percentage of the time available and the number of nodes that's being utilized over a time. Can you comment on that? I mean, so I'm interested in sort of exploring the utilization of the hardware for very different types of applications. And yeah, go ahead.
Again, from our perspective, an application is when somebody deploys an image, an experiment, right? Yes. In terms of utilization, you're right. Some of it is optimal. This middle line here is optimal. Anything below that line is probably utilized more than we would like. And what that means, so when users use Chameleon, they come and they say, for example, I need 400 GPUs right now, okay? And I need them for a week, right? So it's not that there's some application that finishes running and the nodes get returned. They are at the discretion of the user for a whole week, or they can make an advanced reservation. So all the stuff that you have here below this line that I would call optimal, right? So this is the 50% of the time is I would say the sweet spot, right? Anything that you have below here means that when you come to the test bed and you're looking for something, you're looking for GPUs or looking for memory hierarchy nodes, you probably will have to make an advanced reservation because chances are none will be available right at that time. Right, so in a system like Chameleon, in a cloud and experimental system, I would say somewhere around 50% utilization is probably optimal, probably should be the target. Right now, we are utilized above the target.
Thank you.
Okay. Thank you for the questions, by the way. Those were very good questions. All right. Yeah, keep going. Keep them coming. Not this time? Okay, moving on. All right, so how is this? Can you hear me?
Yeah, yes, we can. It's just someone signing in, and that we can
Okay.
sort of silence that bell for some reason. This is a Zoom feature, I guess.
So how is this hardware made available for users, right? How can you get a hold of it? So if you think about the generic experimental workflow, which is how I typically explain it, is, you formulate some sort of hypothesis, then you say, all right, I'm building a new machine learning approach here. I will need a GPU, right? So first of all, you need to see if there is a GPU available, right? So you need to discover the resources. Then you need to say, so I need to get hold of that GPU somehow. How do I do it, right? It's all taken. Everybody seems to be running just now, right? So you make an advanced reservation, let's say, and now you have the GPU. How do you configure it? And then how do you structure the interaction with it? And ultimately, you run your experiment. What can the testbed do to monitor or collect your monitoring results? So we support capabilities in all those 4 stages, right? And we allow you to discover resources. They're described on a very fine-grained. The descriptions are kept up to date, and they're also kept versioned, which is important from the perspective of reproducibility in computer science, right? And I'll talk about that later, but right now, since the beginning of the project, we had over 100 different versions of the testbed itself, right? So anytime we add hardware or upgrade firmware, there's a new version. And then you have to allocate resources. So like I said, generally speaking, you want to come and you want to say, I want the resources right now. I want access to a cluster of 8 GPUs or 16 GPU nodes, right? Or something like this. But it turns out that everybody's using them. So you need to be able to make an advanced reservation, right? That's what we call allocatable resources. It allows you to do an advanced reservation, but then also allows you to manage this advanced reservation. You say, oh, it's not only 4 GPUs that I need, but I also need some storage nodes because that data needs to go somewhere, right? Or come from somewhere. So I'm going to add some storage nodes. Oh, and by the way, I need a VLAN, right? You can reserve VLAN. So for example, we have a limited number of stitchable VLANs that you can use for wide area stitching. You can reserve one of them, make sure that it's there for your demo or your experiment. I need a public IP, right? Let's reserve a public IP added to my reservation. So once you have those nodes, once you have all that hardware, right? It's like putting hardware in your shopping basket. 4 GPUs, some storage nodes, IPs, VLANs, and now you check out, right? Now you check out, that means you configure those nodes. So they are, of course, deeply reconfigurable. As I said, we've got appliance catalog. Appliance is a generic name for an image, right? So you can have appliances, but then you also can have orchestration templates that allow you to create virtual clusters, and that's also called appliance, a generic name for image. You can snapshot them, save your work, right? So you spend 2 days configuring your image. You don't want to ever spend those 2 days again, right? You want to save it next time you start from that image already configured. Orchestration, which allows you to deploy construct like virtual clusters, or maybe you deploy a configuration in wide area network, right, over TAC and University of Chicago and your own institution. Orchestration allows you to automate that. But integration with Jupyter, about which a little bit more later. And we've got support for stitching and something we called bring your own controller, right? Bring your own controller allows you to create your own controller that works with the Corsa switches, plug it into the Corsa switches and do an interesting SDN-enabled experiment. And then we have fairly standard instrumentation collectors, which collect not just the metrics that you have access to, but also, for example, power metrics that you don't have access to, and then you can retrieve them via our aggregator, right? So this is our view of what a deeply configurable testbed provides. Okay, and just a quick walk through different types of experiments that our users have done on this testbed over time, right? So we're going back to right to the beginning of the testbed. One of the first students who was working on it was Yu Zhu. She was a student from University of Pittsburgh, and she was comparing HPC applications in virtual machines versus HPC applications in containers, right? So the performance of containerization versus virtualization. She actually found that everybody expected containers to do better, but actually virtual machines were doing better for reasons of software interference. And she needed bare metal reconfiguration. She needed to be able to start from custom kernel. She needed serial console access a lot, which we know very well because we didn't provide it at that time. So it all went through the help desk. She needed to save her work, support for large scale because those were HPC applications and up-to-date hardware. Right, so you've got Yu here showing her poster at supercomputing. Similar types of experiments, my colleague Swan Peranu from Argonne, he is designing exascale operating systems, right? So at Argonne, we have the Leadership Computing Facility, also one of the top 10 supercomputers in the world. This is, by the way, the machine room in which Chameleon hardware, University of Chicago Chameleon hardware is located. And so in order to design those operating systems, he needed bare metal configuration, boot from custom kernel, but then he also needed fast reconfiguration, not just be able to reconfigure them, but fast, because what he was effectively doing was a parameter search over many different parameters of a kernel, right? And of course, he needed hardware counters, information from that, and access to the same infrastructure for multiple configurations, collaborators, which meant sharing, right? And so that's, as a shareable instrument, that's something Chameleon is very good at providing. Classifying cybersecurity attacks is a completely different type of project from University of Arkansas at Pine Bluff. It's a small but savvy team, and they were classifying cybersecurity attacks. Many on the team were students, and what they really needed was easy to use OpenStack installation. So that was KVM installation I mentioned before. We support that as well. Pre-configured images, and again, access to the same infrastructure from multiple collaborators. Another example in networking, this is also a supercomputing example, as one was from supercomputing as well. This is, I think, supercomputing 16. A team building virtual software-defined exchanges that broker trust between different network enclaves, right? So like you can see on that picture. And to support that type of research, they needed the ability to create VLANs dynamically. They needed to be able to combine them into wide area circuits. In other words, they needed support for network stitching and for managing of complex deployment, right? Orchestration. They had a deployment here, deployment there. You can see they've got 4 different enclaves there that they are negotiating trust between. Was important to automate that deployment and have it pop up when you need it. Data science research. This is a couple of our students. They are both undergrad students, and they became ACM Student Research Competitions semi-finalists. They were both working on our GPU cluster, and they needed to, of course, those GPUs, but then also interesting storage and access to appliances and orchestration, right? So those were undergrads. Adaptive bitrate video streaming. This is a very interesting project by a student from University of Massachusetts Amherst. She has since graduated, but essentially what she was doing is adaptive bitrate video streaming, and she had this interesting experimental configuration that you see on the picture there, where she needed to, adapt to different quality of network traffic. So she had to create 2 network circuits, one with quality that was reliably good, one with quality that was reliably bad, right? And she was validating her algorithm over that and making sure that it could adapt to the badness. She was using our bring your own controller feature, which allows you to create your own controller to write SDN SDN controller specific for her experiment. And she was exploring multiple connections between the sites. So there's a link here to Vimeo, where we actually made a screencast of her experiment, because how she did it, and I'll come back to that, is even more interesting than what she did. And then last but not least, experiment on power management from the University of Chicago. This is a paper that was became the finalist for Best Paper and Best Student Paper at Supercomputing 19. And it needed support for large-scale experiments, also support for orchestration and management of automated management of complex appliances, and then interface to the power metrics that such experiments need to gather, right? So interface that we provide specifically to our hardware that supports power management. Chameleon is an open platform. As you can see, unsurprisingly, most of our use comes from the United States, but we do also have some use from South America and Europe, as well as Asia. So it's also available to international collaborators if you have any. And then moving on to the shareability of the instrument, right? So how we implemented this instrument to provide sharing to users. So first of all, a big factor there was basing our infrastructure on OpenStack, right? So this means that we're working with a mainstream project, and that means that it's, generally speaking, very familiar to both users and operators, right? If it's not familiar, then they are learning OpenStack, they're learning cloud computing and developing transferable skills. It's very interesting. We actually had many students working on Chameleon last summer. We called it the Summer of Chameleon, right? And I'll tell you a little bit later about what they were working on. But it was interesting that after the summer, there was a survey, and many of them said that what they learned was OpenStack, right? So that was cool to see that they internalized, that they got something out of it that was largely orthogonal to what they were doing. But the familiarity is one aspect. The other is that we work with a very large community of contributors and, very importantly, reviewers, right? Thousands of contributors and reviewers. That means they're putting out innovative, interesting features all the time, and we're just sitting there and waiting for those features to fall into our lap, more or less, right? We just adapt them to our users. We get access to existing documentation and support systems, right? If there are problems, we don't have to necessarily solve them ourselves. There are new features that come all the time. Here's an example of a few features that we got by just upgrading to the next version of OpenStack. And there's opportunity to contribute, right? I already said at the beginning, we contributed a significant component to OpenStack. An example of why this was all good. So systems like Chameleon and similar systems are, of course, very, very difficult to upgrade and to maintain and to support. That's because there are many moving parts, right? They are complex because they solve very complex problems. All this, deploying bare metal images and giving access to users, as you pointed out, there are security issues with that, right? That has to be done carefully. That means that maintaining a system like that is expensive. And the first time we did an upgrade of Chameleon, it took about 7 months. And to be fair, in those 7 months, we streamlined a lot of our operations functions. But we now moved from those 7 months of multiple people with high level of expertise working on it to one person with low expertise working on it in under a month, right? So how did this happen? Well, it happened because there are others who work on OpenStack deployment as well, and we were able to beg, borrow, or steal their expertise. A few words on it on the next slide. Support and reliability. We have streamlined monitoring and alerting. So we've got, of course, smoke tests, but we also have live monitoring with coverage and centralized logging, right? So we run something called Prometheus, which I think is standard in most systems. It funnels output to Grafana, and we have lots and lots and lots of dashboards that we look at to see, what the traffic on management nodes is and so forth, and look at whether something is amiss, right? But once alerts tell us, well, something is amiss, we have runbooks and hammers to fix the testbed. Runbooks is documentation on how to fix it. Hammers are bots that actually go and fix the testbed automatically. See, I'm falling behind a little bit. And then we have a process around maintenance. So just to give you a little idea, this is what it looks like. This is our Grafana output that looks at various metrics from coarse grain to very fine grain metrics. And then we have alerts based on those metrics that trigger whenever there's something bad happening on the test beds that you can click on, and they take you to a run book, and that tells you, here's the administrator documentation for this specific case, and then you can fix it and push that fix and alert everybody on our Slack that this is what happened. Now, a couple, one old thing and one new. One thing that we did is we packaged Chameleon, and that packaging is called Chinabox, right? And we call it Bring Your Own Site. So if you want to become a Chameleon site, so to configure your own Chameleon, you could, right? This is based on Koala Ansible. This is the innovation that we got from the community that allowed us to do those upgrades very quickly. And it also packages our operations model. So it packages all of that stuff of monitoring and remediation that I just showed. And you can take it, you can configure an independent testbed for your own users, right? So then we don't provide the portal user management or anything like that. You can become part of Chameleon, in which case we do provide those things, or you can become a part-time associate, right? So part-time you're part of Chameleon, other times you use your hardware for your own things. We first released this a couple of years ago, and we currently have an associate site at Northwestern, so it's actually undergoing a transformation, and we will announce that this month or the next month. And then National University of Singapore also deployed Chinabox. But Chinabox is still, you know, it's a whole site. You've got management nodes there, you've got a lot of moving parts. Sometimes you don't want to have a lot of moving parts. Sometimes you just want to add one node, right? This is why in phase 3 of Chameleon, we're implementing something called Bring Your Own Device. And that's also called Chi at Edge. This is specifically geared towards adding edge devices, right? So any user could say, okay, I am working on this innovative edge device that I want to add to the test bed. I want to download an SDK, put it on this device. It calls to some virtual site operated by Chameleon, and it becomes part of Chameleon. So it, in other words, implements all that cycle that I was showing you earlier of discover resources and allocate them and configure them and monitor stuff on them, right? It's gonna have access to all those services, right? So you operate the device and add it. We operate a virtual site for you. And like I said, it's targeted at less powerful, more heterogeneous devices. Now, there is a change that this involves. So like I said, Chameleon is mostly operated on the bare metal level, except we do have a couple of racks that are operated via KVM, right? So those are different definitions of isolation between users. Bare metal is performance isolation, KVM does not provide that, right? So now the question is, how are we going to configure those devices? Well, for some applications, for example, for new nodes in machine room, it's gonna be bare metal, right? So it's gonna be relatively easy bare metal type of thing. Somebody else adds an edge device, a TX2 or a Jetson device, right? One of the NVIDIA little things. They're not server class, right? They don't necessarily support a bare metal reconfiguration that we can provide easily. Maybe we'll make them allocatable via containers, maybe via static use. The jury is still out on that. And again, if you're interested, let us know. We'd love to work with you. But you know, think about a world where a supercomputing center can buy a lot of very expensive hardware and say, maybe we can make it available to computer scientists for a couple of weeks before we make it available to domain scientists. Maybe computer scientists can come up with some interesting methods, but it's going to be available differently. It's going to be available via bare metal configuration, whereas later on, it's going to be available all the way we always make things available, which is via batch, right? So there is potential for people to make things available on an ephemeral basis, interesting hardware on an ephemeral basis with very little investment. All right, and now switching gears and exploring the third dimension, after I almost ran out of time, but I'll try to go over this quickly. Imagine now a world where experiments are as shareable as papers today, right? So when I write a paper, I go and make, I do a literature search. I look at various different papers, see what others have done. It informs my approach. Imagine if I could do not just literature search, but actually run what all those other people did. And I could run and I could change this parameter and that parameter and change all these parameters all the time. And then I might come up with an idea, right? I might get a more intuitive understanding of what it is that they have done. And it turns out that actually, well, nobody does it today, but there isn't much of a gap between that picture and what we have today, right? So first of all, we have now, thanks to NSF, instruments held in common. Instruments like Chameleon that anybody can access for research purposes, such as repeating somebody else's research, right? Well, that's the necessary condition, right? Because it's no longer the case that I have access to a cluster of GPUs and you don't, because it's in the basement of my department and you don't have it, right? Now everybody has access to a cluster of GPUs. The other thing is the cloud model. Clouds allow you to deploy an environment onto the hardware rather than a job onto something that somebody configured for you, right? So disk images, they give you orchestration templates. You can not only get the same hardware somebody did, but you can configure it in the same way very easily using mainstream tools, right? So you can easily recreate their experimental environment. And we haven't done anything yet, right? We're just using clouds. We're just using clouds the way they are supposed to be used. So what is missing, really? I mean, we're almost there. I think that three things are missing. One is telling the whole story, right? So we have hardware, we have now experimental containers, so we have configured this hardware. Now we have to run something in it and analyze the data and produce a graph. And something that puts all those things together is called literate programming. And it was first described by Donald Knuth, who else, right, and came up with this. And then the other thing we need is the easy button, right? So all those things, they have to be not only doable, but they have to be easy to do, right? And easy to package in such a way that somebody can repeat them. And those people have to be able to find them easily, right? And get credit for it easily too, and reference them easily, right? Very important that everything should be easy. And there's a bunch of nits and optimizations about how we do this, how we do that. I won't go into this. I wrote an editorial last year that kind of summarizes most of those things if you're interested. So experiment sharing for Chameleon, like I already mentioned, hardware is versioned. Right? Images and orchestration templates, we've got lots and lots of them, thousands of them. Our users created them. They're also versioned. We have integration with Jupyter Lab, which I'll talk about in a minute. And now we also have mechanisms for finding and publishing that research, right? So I always say that a testbed is a player for research. Like, you've got a bunch of long players and you've got a player for them, you can play them. If you don't have a player, you can't play them. So packaging shareable experiments, how do we do it easily? So first of all, we have literate programming. Jupyter is nothing else than an implementation of literate programming, combines experimental storytelling, process via code and results. It has one problem. When you run the code via Jupyter cells, what they do is deploy a container on the back end, run everything in the container, right? But the container, for our users, container is not enough. Our users want something that looks like this. You've seen it before, right? It's a distributed environment with different network circuits. This is not a container. It's not a Docker container. This is an experimental container. They want to create those containers. So what we did is we integrated Jupyter with Chameleon. So on a credential level basis, when you log into Chameleon, you're logged into your Jupyter notebook, and conversely, your Chameleon credentials are implicit in your Jupyter code cells, right? So that you can go out to the testbed and create a container like this via a Python program very, very easily. And I said the student who created this diagram and the experiment described by it did it in a very interesting way. She was our first user for Jupyter to Chameleon integration. So here's the link to the screencast again. It's very interesting. And there's also a paper for that as well. Now, you have to share those experiments somehow. And originally we thought, well, we just publish those experiments to, we'll just publish those experiments to Zenodo. But when you publish to Zenodo, it's a digital publishing platform. It gives those experiments a digital object identifier. They become citable, and they are there, for all posterity, so to speak. A lot of our users are not ready for that, and it became particularly obvious this summer when we worked with a bunch of students, and they were packaging experiments into Jupyter. They were packaging various experiments from various foundational papers so that people can repeat those experiments. And they didn't want to, they were never ready to publish them, but yet they needed to share them somehow. They needed to share a partial result. So what we did is very quickly implemented Trovi. So you can think of Trovi as a kind of a Google Drive for sharing experiments that is integrated with a testbed, and you can run the thing that you share on that testbed. You create a bundle, you edit sharing, you can share with just your buddies, or you can share with the whole world, and you give it the right tags. And based on those tags, people then can find those artifacts and make them, deploy them on Chameleon. And then finally, our publishing cycle. So Jason mentioned in the introduction, I'm very interested in how we publish research, created a journal for publishing software, but more interestingly, how are we going to publish experiments, right? So on the left here, you see some pictures from our traditional way for how we publish and share research, but what is a way of sharing it digitally, right? So it seems that something like a testbed or a place where you can replay that research is going to play a role. Why? Because when I read a paper, I'm just using my eyes, right? I'm very well equipped to read a paper. I'm not necessarily well equipped to run a machine learning experiment. In fact, I'm not equipped at all, right, by myself as a human, right? But a testbed, now a testbed is very well equipped for that job, right? So you need a reader, a player, right, for that packaged machine learning experiment, right? So I think in that new evolving digital sharing ecosystem, or you can think digital publishing ecosystem, we will use something like Jupyter to package experiments. We will use something like Chameleon to have a shared platform to replay them. And we will use digital object identifiers and things like that to cite them, right? So I said Zenodo does not cover all of our needs, but yet it's a very important element in the publishing cycle. Okay, phase 3 advertisement, right, very quickly. First of all, the first thing that changed in phase 3, and it already changed, is Chameleon is now accessed via federated accounts. That means you don't have to create a new Chameleon account. You can come and log in with your institutional account, or with Google account. You can also log in with the Google account, right? You can create an account if you want to, but you don't have to. That federated identity also means Chameleon is now federated with a bunch of other testbeds, right? It's federated with CloudBank, it's federated with Fabric, even before Fabric was deployed, with ExoGenie, with all the and Genie, with all the places that we all know and love. I already talked about what's coming down the pipe with new hardware, new capabilities. Well, of course, federation, bring your own device or Chi at Edge, networking, new networking capabilities via allocatable switches, and a lot of core capability improvements that our users specifically asked for. On infrastructure levels, we're going to be making improvements to Chi in a Box, and we're going to show deployments of that. And we're going to be developing better methods of experiment packaging and publishing and discovery, digital experiment libraries, engagement. The Summer of Chameleon that I was talking about produced a variety of experiments from those foundational papers. For example, AlexNet, the AlexNet paper from 2012, we packaged the experiments from there, and it takes only an hour to replay those experiments on Chameleon. And how much more fun is it to learn about something from a paper that revolutionized an area rather than from a canned exercise, right? So feel free to browse them, feel free to use them in your teaching, or to tell students about research, or tell students how to introduce variability into experiments. And a few parting thoughts. First of all, I talked at the beginning about Chameleon being something that adapts itself to your experiments. There's another meaning of Chameleon, another way it's a good mascot for the project, and that way is that science constantly changes, right? People are users, and anyway, every day want to try something new. And every day they come up with something that we're not prepared for because nobody thought about it before. So really, operating a test bed is like laying the pavement as you walk on it. And it's a lot of fun. We like it. So Chameleon is a shareable instrument, but also a sharing platform, also a platform on which you can share your experiments. We care about making reproducibility sustainable, right? And packaging your experiments is one thing, and I understand a lot of conferences encourage it, but if we don't have a marketplace, a demand for packaged experiments, right? If it doesn't feel natural to actually reproduce somebody's experiment, those efforts will fail, right? It's all right now, the efforts are concentrated on the supply side. We're hoping that they will also emerge on the demand side. And all we do need now is a critical mass of content. So we need you to pack your experiments, make them available, tell us if it's hard. And this is all I have, right? We're chameleons, we're here to change. Please come and change with us.
Thank you, Kate. Thank you for the talk.